and thanks for the invitation to the meetup. Very interested in seeing what everyone thinks about my presentation, so very open to feedback. I think the best thing may be to save the questions in the chat for the end, just because I kind of under-timed this, I think. So I'm going to try to get through this as fast as I can, which means it may be best to save the questions for the end. All right, well, let me go ahead and increase this. I assume you can see the screen. Cool.
Yes, looks good.
Awesome. All right, let me hide this little thing here because hide floating media controls. Awesome. So thanks again for joining my presentation. Thanks again, Seth, for allowing me to present. Today I'm going to present on translating electronic documents, which is also known as machine translation. And I'm going to specifically talk about the kind of work that I do, which is really low resource machine translation. And go there. So who is this dude? I don't normally wear a tie. I just do that, as I call it, my funeral suit. So I'm, again, John Ortega. I have a PhD in machine translation, more specifically natural language processing, computer science as a high level from the University of Alicante in Spain. Also worked on my postdoc in Spain and postdoc here in the US at Boston, and I've taught at several different universities. All of those are on the screen there. So my kind of verticals, what do I really work in? Natural language processing. So I don't just do machine translation. I also do NLP, machine learning, and I've done a lot of software engineering in my time as well. So I guess the question really is about like, what about translation? What am I actually going to present today on translation? I think what I'm going to do is try to cover the evolution and just to really kind of, from the standpoint of the history of MT, talk about experimentation, the different types of MT, and then cover the kind of more interesting things that everyone seems to be interested in these days, which are the transformers and large language models and zero-shot translation. So I'll start from the beginning, which kind of starts in 1940 and goes all the way to 2023. Normally I play these videos. I don't know. Well, maybe I'll play a little bit just so that you know, how did I get into MT? Well, my kind of first real kind of touch with MT was back in 2011 or 10, when I began working on trying to solve this problem, which in my case, I have family members that are from this area in Peru, where they speak a language called Quechua, which is an indigenous language from Peru. And while I was working my master's degree at Hofstra, I started to find other languages that were high resource languages, which I'll get into a little bit. But basically, the one on the left-hand side is which I'm going to play is the Quechua text or Quechua video, and the one on the right is the Finnish video. This is just so that you can understand kind of how the languages sound, and hopefully kind of pick up on some differences, and actually more than differences, similarities. So here's the Quechua text, or I keep saying text. Hopefully you can hear that.
Provincia de Huare, distrito de Chaná, Santa Cruz de Pichiu, pueblo de Pichiu. Huisla y Huancayo, 6 no marca, Huisla.
Chuma como Maure. Lindo, lindo, taita marca.
Huisla de marca Pichiu Nishancho, Pichiu, Atka, Ichicha Pajarito, Pichiu Chanqui. Huisla Nami, Atka, Kaino Arbolito, Kuna Huisla.
So that's just a real quick excerpt. I'm not going to play the entire video. And then Finnish, which, believe it or not, is quite similar in many ways, grammatically and morphologically speaking.
Jonkun tavalla, ja se ei ole niinku outoa, jos sä oot vaan hiljainen, että meillä ei oikein ole sitä niinku awkward silence, mitä amerikkalaisilla on. Niin myös se on aika erikoista silleen, että mä oon tottunut niinku amerikkalaiseen kulttuuriin, koska mä oon asunut täällä niin kauan aikaa.
So it's actually kind of funny because both languages steal words from high resource languages. So Finnish, oftentimes you'll see some English words show up, and then Quechua, you'll see Spanish words show up. So the idea was that I wanted to figure out a way to translate Quechua to Spanish. There were no real resources out there. And so I found Finnish to be the closest high resource language that had a little bit of resources. And I'll go into that a little bit later. So where did it originally all start? MT in general, not just from my work, but in general, MT was really kind of set up as a task by Warren Weaver. I don't know who, well, I guess this is some of you are probably from New York. So you may have heard of Warren Weaver just because NYU has a huge hall called Warren Weaver Hall. And that was actually dedicated to this person who really was a champion of computer science, and more specifically, kind of helped set up MT as a task. Now we go from 1940s all the way to today. We've seen several different types of systems, starting off with kind of, and not even the rule-based systems, very much just a challenge in the first systems, which were even before rule-based systems. They were just using dictionaries from from the source language to the target language. Then the rule-based system came out, and then example-based, statistical and neural-based, and finally kind of neural-based systems that we're using today are based on large language models. So if I talk about a high level, where does all this sit? If you look at the field of AI, it's got many branches in it. I would say the NLP branch really covers machine translation, a few of these other things. Some like to discuss that and say, well, wait a minute, deep learning is part of NLP, and yes, it is. And so is speech to text in many ways. But I think MT definitely clearly falls in the NLP branch of things, and more often than not includes several tasks from NLP, not just taking words and finding their translation. A lot of the things that MT has to do, you will find in several NLP tasks like information retrieval, question answering, and so forth. Now, what does it involve? I know this sounds straightforward and probably almost self-evident, but the idea is that you have a source sentence, or oftentimes called a segment. For example, the dog barks at night. Then some MT system is going to take that source sentence and translate into a target translation. And so here you see the Spanish translation for the dog barks at night. More often than not, we kind of treat MT systems as a black box. So most of us will end up on translate.google or Bing, or one of these kind of web interfaces that have been highly marketed, and we kind of just use these MT systems as black boxes. But little do we know there's a lot behind them. It's not just throwing together like a ChatGPT system or something like that. Now, when I talked about the three paradigms, yes, there's the ones I'm going to cover today. I'm not going to cover example-based, but I will cover rule-based, statistical, and neural. This is kind of how it looks, just looking at the high-level paradigm. So RBMT, you've got a rule-based machine translation. You've got three kind of types there: direct, transfer, interlingual. Statistical machine translation, you got word-based and phrase-based systems. Most of the time, you'll probably hear phrase-based systems like Moses. And then finally, neural machine translation, which I think these days, basically they're either based on a CNN, an RNN, or a transformer of some sort. What's actually hard to believe is that we don't, in the wild, meaning not in the wild, in production at companies, we don't really use NMT as much. So one of the latest research results here in this, you can go to this URL if you're interested, gives you a little bit of background on how much we actually use NMT, neural machine translation, in production level systems. So reality is we actually use a lot of rule-based machine translation still, quite a bit of statistical as well, and kind of low use. Now this has changed in the last 2 years. I mean, I would say this is more probably like NMT might be more like 15% at this point, but it still hasn't taken over the industry as far as MT systems are used. And systems like Google Translate, for example, use a lot of NMT, but they still have a lot of RBMT, especially for the low resource machine translation systems. So then one would ask, which way do I go? Like, how do I, for some low resource language, in my case, when I built the Quechua Finnish system, I had to come up with something that would work for both. Quechua and Finnish, and be able to go vice versa, meaning from source to target and target to source. So, the first thing I did was end up with, I guess, this is 12 years ago, and there wasn't really a lot out. There was just statistical machine translation and rule-based machine translation. And RBMT kind of works like this. So you basically read in a source language input and you add some type of rule to it. Oftentimes, these rules can be generically done in a config file. Once that rule's been applied, you can then follow the steps through digesting the rule into some type of catalog. And then there's typically some expectation maximization step that will take all the rules in play and apply it the best it can, giving us some final output towards the target language that will hopefully fit the morphology. This is kind of what probably the most used RBMT system out right now is called Apertium. This came out of my university, University of Alicante. And there we have source language text, for example, and it goes through a ton of things here. When I say things, I'm talking specifically about modules of a process. So you've got formatting, there's morphological analyze, part of speech tagging, lots of other pieces of this pipeline, which basically take it to the final step, which is a reformatter than target language text. So an RBMT typically looks like this, and it uses hand-tailored rules. So if you were to go to apertium.org, you could actually put in for low resource languages that you might speak. You may want to help out the community and add a rule or two in there. And this is one of the things that they do at Apertium. So my first attempt at the rule-based machine using an RBMT, which wasn't Apertium, it was just kind of using what was out at that time, which was just a way of aligning things. It didn't even actually translate at that point. Was using this, creating some rules based on alignments, meaning I had in one language something like this. This is like my son, obviously French to English, but the idea was the same. I was trying to go from Quechua to Finnish before I did Quechua to Spanish. So it looked like this from my project, and this is one of the papers I've written before, where there's an alignment error rate, and we're given basically all of the probables or all the possible links, and then all the annotated links, and we try to come up with the best. Now, of course, this is not a machine learning model. This is just using rules. So given some type of new potential text to align, I align them, and then finally I get some final score of how successful I was at aligning them. And so in my original work for rule-based machine translation, I actually got a lot of views and so forth on the article, and it still to this day gets quite a few views. I found that the best kind of alignment out there at that time was 85%. This is the error rate, meaning it was pretty bad. Spanish to Quechua from the Zurich results. And my first attempt wasn't that great either, 85.62. Later there was some inflectional groups, meaning they group rules together into clusters of groups or clusters of rules. So we got 74, or they got 74 there. When I did that with Finnish to Quechua, I noticed a pretty big jump over what they did. So I was getting 64% error rate. And then finally I lowercase things, built some better groups, and I was able to get about 61. So that was my first intuition into finding that, similar languages, whether it be rule-based machine translation, statistical, or neural, actually seem to do better. And it's probably based on the idea that when two languages are similar in morphology, they tend to work better in translation. Now, after the rule-based came out, I also worked on some statistical-based stuff, statistical-based machine translation. This was really came out already in like the 90s, right? The mid-90s or so. But the big system that came out was scored on what's known as BLUE. Now there's many more scoring mechanisms for translation, but this was kind of the main one out of IBM. A person named Salim Rukos and several others at IBM created this great idea of, if I have the human annotation references and the target translations from the system, then I can measure how well the system works. And that's where they started kind of really being able to statistically or look at the statistical-based machine translation systems and score them and make them better. And that all happened around, I guess, BLUE came out in like 2001 or so. And so the statistical-based system, since they were able to begin to measure things a little bit better, they were based on phrase-based tables. So you had things like this, or Maria no daba una bufetada a la bruja verde. And so then I had like Mary, that was obviously, there was only one option there. But then I'd have several options for the next phrase. For example, no would be not, did not, no, and so forth. So you ended up building a phrase-based table system that would basically get you the best translation according to probability. And this was known from IBM also, because at that time, IBM was the big research group around for NLP. This was known as IBM System Model 1 and then 2. And so basically that all depends on what's known as the expectation maximization step for the decoder. And oftentimes you hear this as a beam search. So SMT was found to be pretty good. And actually, if you look at the more recent comparisons to neural machine translation, for certain languages, I don't have them listed here, but I think it was Ukrainian to English and other low resource languages, SMT still beats out the best NMT systems. And in some cases, for example, this one, there were 6 points of difference. So quite a bit, you know, you can't just assume just because large language does well, do well in English, that they will do so, you know, do so well in other languages. So anyway, SMT was where I began to focus more of my efforts. So I met these two very smart people. One of them is Philip Kuhn, who works at Johns Hopkins now. Back then he was at Edinburgh. He joined there specifically to work on the machine translation problems. And Rebecca Knowles, who was a co-author of mine as well. And they took those SMTs with the blue scores and started comparing them more specifically to neural. And what they found was that at a certain point, yes, neural definitely does better. And you see here, I got about 31. But before that, and this is the corpus size, when I have smaller amounts of data on the order of, say, you know, 10 million sentences, parallel sentences or so, it stayed the same. It was still the case that both phrase-based or with big LM and phrase-based statistical machine translation systems were still actually better, even on, you know, English to German, which was the big task at the time. So that was a big breakthrough. And then when it first came out, and they came up with a paper called 6 Challenges for Machine Translation, which basically sparked up the NMT world to try to beat this whole to show that they could, with smaller amounts of data, get better results on blue. Now, so that definitely led to more research in neural and to where we are now. Of course, NLP is, for the most part, using large language models. The problem we have with neural machine translation, I think we're seeing this more and more. I mean, you know, you can see this on LinkedIn just from anyone posting. Typically, the problem is it's costly, right? So NMT takes a long time to train, and it costs a lot, meaning you have to have quite a bit of resources, and typically smaller academic universities don't have those types of resources. Also, the models are very complex and so less interpretable. Yes, they give high quality. So blue scores, for the most part, despite what I showed before, they get higher quality in general for English to Spanish, English to German, and so forth. So NMT is great, like when you have a lot of data, and I mean a lot of data, and a lot of resources to run and train those models. So I think that's one of the big disadvantages to NMT. And so you know, you look at the comparison. Here we are now in the 2023. But before we even got to the transformers where we're at now, back in 2016, 17, there was Vasvani, the transformer idea came out. But before we did that, we were still working kind of on the edge of moving from phrase-based over to neural machine translation. And so we could, with neural machine translation, we were able to capture semantics, which really made things different, right? So for phrase-based, we had syntactic differences between phrase tables where you picked up Maria, Mary, and so forth. But we did not have that whole idea of, which we all kind of probably have heard of it by this point, of word embeddings, which is, you know, I find relationships such as queen to king, man to woman, and so forth. That was obviously found in 2016 by Mikolov at Google. They put some of this stuff into the ideas of neural machine translation. And so the encoding of languages looks something like this for NMT, and then it gets decoded into a target language. And all of these words, for example, are carrying information via word embeddings. The nice thing, again, about this MT system, you had free neural machine translation systems out there. They came with pre-trained word embeddings already, so you just basically install it. You know, if you're in Ubuntu, it's just app install OpenNMT, and you have an entire NMT system that works for pretty much, you know, I think something like 100 languages or so, from the standpoint of view of you know, the languages that it could translate. That all happened in more or less 2017. And so we were still, you know, myself with Catch When Finish, I created a paper with NMT as well. And we saw things like this, 18.5, 19.5, blue scores, which is actually pretty decent for low resource things. And so as we kept moving forward, you know, I had another project that I worked on where it was, you know, I just compared and contrasted all three of the different types of systems. So if you look here at the bottom, I've got rule-based, SMT, and NMT. And so in general, for example, MT output, the rule-based system for word error rate's great, but for blue, it's not that great as far as here. So what we really see on MT output for things like this, now this is English to Spanish, and of course using a very specific a technique called fuzzy match repair from the translation system. NMT still gets beat out by SMT for small phrases, and of course less data. So in this very particular experiment, there was 70,000 training sentences available. So it didn't, again, SMT kind of did very well there. And of course, you look over several different language pairs. In some cases, neural does better, you know, more than others. But then when you do comparisons with humans and so forth, at least in my case for Catch What a Spanish and Catch What a Finnish, I found more often than not that the statistical machine translation systems or some hybrid of an NMT SMT system work better. Now I'm going to try to skip over this or go through this really quick. So, you know, after we got out of NMT with just CNNs, RNNs, and your typical LSTMs, we end up with embeddings and transformers. Embeddings, I think most of you probably get a good idea of how that goes. So typically you're going to train some MT system with word embeddings as input, meaning each word is represented by some matrices or vector of numbers. So that all becomes part of the training. It also becomes part of the classification. I do not lose the idea that each word is represented by a bunch of numbers. And then I use those as input for machine learning algorithms to create a model. And of course, this intent or LALO could be either the target sentence, or it could just be an NLP, some intent that you're trying to solve for, like some question answering or chatbot. So word embeddings, what do they look like? This is kind of going back to Mikolov and so forth, and just how one could easily, like, say, scour an entire internet like Google did and give us a whole lot of word embeddings, which are based on context. They look kind of like this if you haven't seen them before. And the nice thing is that you can load them really easily into this OpenNMT system that I spoke about before. And you know, you have this Google word embeddings, which are like 300, I think 100 billion words or something like that. And those can be used as input into the embeddings for OpenNMT torch, and so for translation. So what happens, or how well do they perform? Well, with word embeddings, OpenNMT with word embeddings included, do really well on languages like Romance languages, and not too bad on actually low resource languages in general. So, you know, Spanish, French, Portuguese, Italian, some other low resource languages as well. But when you look at very specific languages like English to Russian, again, back to English Ukraine from before, they still don't store as well as, say, the rule-based or statistical-based systems. So that kind of led to, you know, where this whole kind of renaissance, I don't know what you want to call it, but the idea really is that since this paper, the Vasvani paper, and of course there are more authors, but we all just call it the Vasvani paper. Lots of other people worked on this paper, but Vasvani was definitely known for it because He was the first author. So Transformers came out, and of course, this really changed the game. And that's not just for neural machine translation, but for NLP in general. And so it did that by, you still kind of kept this encoder decoder idea, but then all of a sudden, and that's where the attention is all you need comes from. I have attention across the board. So then I can easily, given some sequence to sequence model, come up with better target sentences than I did before, because previously for neural machine translation and everything else we did, it was taking in kind of had an assumption that you were going to lead from left to right. And with the newer transformers and sequence to sequence model, even for zero shot, meaning languages that didn't have any data available, they still did better than rule-based systems. So this really changed the game. Again, these are just some of the highlights of what's there. So if you look at here, this is where, if you go and look at the papers from how a transformer is really kind of done for encoding, decoding purposes. The left-hand side here, where the red box is kind of where the inputs go, you have some embedding. Again, this is like a word embedding of some sort. And then there's this nice feed-forward network with some attention. All of that gets passed out to the output embedding over here, which of course, again, is very similar. I've got an attention, two different attention layers along with some feed-forward output, and finally a softmax. So what does all this mean? Well, basically, I'm able to do encoding, decoding with several kind of, let's call them attention nodes available. And then it's not just like walking through the previous SMT decoding with Maria, Mary, and then trying to figure out which one. I've got all of this information. It's taken along as I learn things. So anyway, Transformer Zero Shot. If we look at this WMT, this is the biggest conference out for machine translation just last year. Some of the results are here. This is all mostly transformers. And if we look at blue scores, right, everything in these blue columns, pretty high in the sense that these are even for low resource languages, such as this one, HSB Sorbian, German to Sorbian. That's German to Sorbian there. That before these types of scores were unheard of for Sorbian. Sorbian, typically you would get somewhere between 10 and 20 blue with the rule-based system. So this has really changed the game. And to be honest, large language models on top of the transformers, so the large language models are generally built on some type of transformer architecture like GPT and so forth. They really are able to do wonders for machine translation. So for zero shot, meaning even those languages that don't have much available, I've published a lot on this. Obviously, these are the articles that I've published on this stuff. Even with few shot, pre-trained language models such as the Facebook Seamless 4MT, they all use pre-trained language models that allow you to translate multiple languages to multiple languages, all the way up to 200 low resource languages. So I think that's one of the best MT systems open source out right now for low resource languages. And they all use some type of pre-trained language model of millions and millions of monolingual data, meaning they've gone and scraped lots of low resource languages, websites and things like that from the internet, and created this really nice kind of large language model. So again, this is one of those places where large language models or pre-trained language models has done wonders, right? They've really changed the low resource language world. So you can do things like this. I can, if I have a large language model like that set up, or a transformer set up, I can translate from any language to any language without having to train on either of them. And that's one of the big things about zero shot. As long as I just throw all of the languages into one big training pot, let's call it, I'm able to translate to any language using the transformer technology. So it's really nice in the sense that at this point, if you go use Google NMT, and meaning the website, and they just included Quechua and several, like 13 other low resource languages recently to translate Google. You'll now see there are several opportunities there to add more, and of course collaborate with them. And and I think, at this point, we can almost say that for the majority of low resource languages that have some digital resources to even translate, these large language models are outperforming everything else. Things like this. So for example, when we look at the zero shot solutions here, where transformers were included with the word embeddings and so forth, English to Belarusian, English to Ukrainian. I don't know if you remember from the first few slides, but none of those numbers were anywhere near this. So 20s in blue is not bad, meaning, yeah, there's going to be some errors and it's not going to be perfect, but you will kind of understand at least what it's trying to translate, which if you're in a situation, it's like high risk, maybe someone needs to go to the hospital and you don't know what they're saying. A little bit of something is better than nothing. And so that's really it. So the idea is that, the evolution, we've come since 1940 all the way to 2023 from some very basic ideas of dictionary-based MT to transformer, zero shot, and pre-trained language models, which I think the best system out there would be the Facebook system, which is based on the training of 200 low resource languages in addition to the high resource languages. So we've really come a long way. It's needless to say that we're seeing it. This is kind of the last year has really changed things. So not only has it changed the question answering and chat and all of that, but machine translation has changed quite a bit in the past few years too. And I think I hope I didn't go over time, Seth, but thank you again for listening, and thanks everyone for withstanding my presentation on machine translation.
That was
you.
good, John. I really like this topic, and it's something I've been following for many years. But anyway, you do have a couple of questions in the chat.
Oh, okay, great.
And folks can, if they wish to, can use Q&A for the questions. And then if you use the Zoom raise hand feature, attendees that is, and want to ask your question live, I will enable you to do that. Just use raise hand if you want to do that. I'm going to go back off screen. But so, John, you have a couple of questions in the chat. You can see them?
Yeah, I see.
From HV.
Let me see. Let me start from the top here.
Is RBMT
HV to host? Okay, yeah, okay. HV is RBMT bigger in usage because of explainability and classic rules-based systems versus true black box? I think it's a little bit of both. To be honest, when I say both, it's quality, meaning for a lot of specific domains, and this is where large language models don't do as well. So if I'm trying to translate, let's say, an instruction manual for a washer and dryer, large language model is going to do really bad. RBMT in those cases, of course, if you're a translator and you know how to translate, for example, I don't know, an engine part that's specifically from a washer, RBMT will be able to do that. So while it may not be as fluent, meaning it won't be as readable from the end user standpoint of view, some of those words will make more sense than, say, a large language model, which would probably hallucinate on words like those. Another question, will this be uploaded for later? I guess, Seth, yes, right?
Yeah,
okay. So
I'm going to upload the video to nlpxing.com. It's up to you whether you want to share your slides separately.
No, sure, yeah, however you feels best. The next one, consider the rate of improvements via NMT over just the past 10 years or so. Is classical NLT or SMT falling behind? That's a good question. I think there are, if you were to talk to, and where you see most MT really is in Europe, to be honest. I mean, in the US, MT is starting to gain a little more traction, but typically in the US, it's English to Spanish, if anything. It's starting to see a little bit of English to Chinese, but if you think about where it's probably needed the most would be some place like Europe, where there's a lot of high resource languages, there's a lot of business cases and so forth. And so there, you still see quite a bit of NMT from the bigger companies. And I think it goes back down to, and you may remember the phrase table slide. If I have a dictionary of possible words for certain named entities, then I don't have a real way of doing that per se with transformers. Now, I could do a transformer translation to first get the kind of more fluid target text and then replace those words that I know, like those named entities, with the statistical based system. And that's what they do. Oftentimes they'll mix both. They'll do like a hybrid model of some sort.
Yeah, if I could interject, I did some work a number of years ago. Well, not work. I interacted with and produced a few conferences taking place in Brussels with a group called LT Innovate that's headquartered in Brussels. And, a lot of the language translation, machine translation in Europe is impelled by the European Union. That includes not only the high resource languages, but also Luxembourgeois and Maltese and so on. And also, Welsh. And anyway, so I'm going to put in the chat an address for LT Innovate, this organization. So people in Europe in particular might want to check that out. So back to you, John, to check out more questions that have been entered here in Q&A.
Yeah, great. Yeah, that's a good one. LT Innovate, definitely know who they are. Unbabble is really popular right now. So a lot of researchers working on that stuff too. They're out of Lisboa. And then there's Translated. Those are the kind of, and like LT is the other one, which actually came out of LT, the person who helped found that was a person who was on the original Lucy team, which was one of the first MT systems. Oh, there's a bunch of questions here now. Okay. So let me start. So Stephen, actually, how are we doing on time? Okay. Stephen, what is the intuition for why translating Quechua works better than Finnish than Spanish? That's a good question. So in general, for what we found, and this has been found in a lot of research, languages that are similar in morphological makeup, meaning grammar, tend to translate better. And the intuition is it's all based on agglutination, which is basically when I have a root word and I add on suffixes and other things to it, like prefixes and so forth, I have to somehow, the word inflects. So when I add on, for example, dog, I add on an S, it makes it plural. Well, in English, that we kind of know, and it doesn't really change the meaning of the root word. So oftentimes you'll see in NLP, we're really used to just doing stemming and lemmatization because the root word doesn't change much. But in other languages like German, Turkish, Finnish, and Quechua, and most South American indigenous languages, they all inflect heavily when you add on things. So I might add on what's equivalent to dogs, adding an S on to dog and Quechua, which might make it turn into a sheep. So it's very highly inflective and polysynthetic. So both of those languages are similar. And when I did my original master's thesis, I took apart both languages and actually found about 12 different suffixes that meant exactly the same, meaning they inflected the word exactly the same and they were split up exactly the same. All right, let me go on to the next one. Eric, the usefulness of Blue, ignoring his other limitations, heavily rely on having a complete set of reference translation. Yes. Good translation. What confidence should we have? Yes, good question. So we don't have much confidence anymore. And the reason why is because Blue was really created when we were, in the early 2000s, when basically what was out there was RBMT and SMT. With the neural systems, especially transformers and so forth, they've already invented several new metrics. Comet is one of them. The other one's called Meteor. And there's some character-based ones too, just because oftentimes we're just looking at the character level. So this one's CHRF. So typically we'll take something like word error rate, CHRF, Meteor, and the other one I just said, which slipped my mind, Comet, which Comet came out of that Unbabble team. And that the idea there is that they more closely align to neural-based systems. So Blue still, no doubt, it's the kind of de facto standard. I think we've just gotten so used to using it, but and they're not bad, but I think what we've done, or what you seem to see now and more of the machine translation research, is that we get blue scores plus the others, so Comet, Meteor, and so forth, just because all of the systems are now transformers. Aaron, are there any benchmarks for MT versus LLMs? As I've been saying, MTs are far better, accurate, domain expert, blah, blah, blah. For the last 3 years, as the hype curve that LLMs will serve word peace is driving me nuts. This is pretty good. Yes, there are some benchmarks out there for MT. And they are all in the WMT that I showed. So I showed WMT 2022. So if you look up the acronym WMT, it's just the workshop for machine translation. There will be one, there's one every year, and it's always at the big conference, the ACL conference, Association of Computational Linguistics. So inside of the WMT findings or proceedings, there's always benchmarks on both MT and LLMs. Well, I say always, they began last year. HV, is there a metric which suggests that by constraint of topic, washing machine limited domains have the benefits of thus lower dimensional approach of SLT works better, whereas in wider? Yeah, that's a good question. I don't think when we talk about benchmarks too, going back to the other question, I don't think we have a benchmark that would, and that would be actually a good thing to have. I don't think we have a domain specific benchmark. Like, wouldn't it be cool to have the washing machine metric, meaning, let's go out and get like 10 different, domain specific tasks and have these systems run on them and see how they perform. At this point, we don't have anything like that, but it would be nice to have it. Next one. Has there been any work in fusion of symbolic and NMT bases such that rules of fire based on initial assessment of LLMs? There's been a lot of LLM stuff, meaning we've seen exponential growth in the amount of LLM and NLP research. So in the past 3 years, I think it's grown faster. We went from, and actually I worked on a project recently where we took all of the scientific papers, which was from Semantic Scholar, which was 300 million papers. And the matter of just 2 years, that we've added on something like 10 million papers or something, which in history has never been as much. Now, is there some work on specifically what you asked, the fusion symbolic and NMT systems that rules are fired based on initial assessment of LLM? I can't think of any right off of hand, but there might be. It's definitely worthwhile checking. And where you would want to check that would be WMT again, or the major conferences. So ACL, EACL, NACLS, or NAACL. Those three, along with the WMT, should give you some kind of intuition, and they're all open source and free from aclanthology.org. Oh, another question. What are the primary obstacles that limit human quality translation for Chinese? Good question. What is it about the semantics Chinese that differs from the European languages? Yeah, it's the character set, right? So in Chinese, there's typically 2 character sets. I think most, at least, are using simplified Chinese, but even then, 1 character, and all of the MT stuff's been built on space. Right, and that's NLP, not just MT. So in NLP, you will have, for the most part, these systems are created with the idea that one word is separated by space. And so for Chinese, I've built a system called Terminator, which is a term extraction for Chinese. I was a co-author on that paper, and then also for machine translation, we've done stuff in that too. What it comes down to is the which would be equivalent to the beam search or the expectation maximization rule that I showed earlier. Like, how do I know which words align to the character? So in Chinese, which I'm by no means a Chinese expert or an expert in writing Chinese, I would say that several words can map up to one character from some sentence. And I think that whole idea, and it's changing because there's a lot of research coming out of China in the past 2 years too. So I don't know that it's completely solved at this point, but it's definitely gotten much better than it was 10 years ago. But I think the original problem was that alignments in general from even the simplified characters, and actually by simplifying the alphabet made it worse for statistical purposes, meaning my search space got bigger. So I think that was the main issue. I literally work with appliance manufacturing firms. They still use legacy. Yeah. Dragon. I worked at Nuance for a while with Dragon. Actually, I worked there for 7 years with IBM in 2014. But I didn't do translation. I did clinical language understanding. They have all internal SpaceX LMs. Yes, that think you can solve the problem. That's right. I'm swimming in the middle trying to buy a lightweight. So there's definitely a huge group of people out there that are advocates, which I am in one of those advocates for. There's definitely a huge group of advocates out there that are saying, why build LLMs for small problems? And this is becoming a problem if you think about it from just not only the quality standpoint of view and all of the processing that one has to do, but more so, which I know in America, we probably don't care as much, but in Europe, we see this or they see this as a big problem. In Europe, you have to think twice before you go run a bunch of GPUs for some small problem. Because the idea is that you're, killing the world. And so I think at this point, it is kind of becoming that like line in the sand between maybe the more modern and the traditional approaches. Oh, I need to make you host. Sorry, Seth. Seth, here we go. Promote the panelist, I guess. Uh-oh, it said failed to change the rule. Allow to talk. Maybe that was it.
Yeah,
should I try to promote you to a panelist again? Yeah, it won't let me promote you to panelist for some reason. Okay, let me see if there's any more questions here. It's like a LLM cult, indeed. Is it possible that constrained cases call for use of smaller networks, thus making training and resources smaller? Yeah, no doubt. I mean, it's all about, you just think about it, and you don't have to apply a bunch of math to it. It's just, I've got several options, and Bernoulli trials will tell you that, right? Like, how many times do I flip a coin to get the expected outcome? If I flip 2 coins or I flip, 1,000,000 coins, obviously that's going to go way up. Cool. I think I answered most of the questions. Okay. All right, Seth. Yeah, I don't know how to assign you back to host. It just allows me to, I can try to make you panelist, but when I do that, promote the panelist, it says I can't do it. It gives me an error. All right, so good. Seth says we should be wrapping it up. Yeah. All right. So if there are no more questions, to finish out the catch with fish morphological, is there some criteria that could be generalized and automated? Yes, definitely. And so if you were to go look at my Google Scholar, there's a paper that I created. It's called, it's actually based on a technique called BPE, byte pair encoding guided. And so I specifically, so the way byte pair encoding works, it typically will try to separate words up for you because it has no other way to do it. And since the MT systems use spaces to separate, it tries to separate the input beforehand. And so I take the the suffixes from both of the words or both of the languages, Finnish and Quechua, and try to match them up beforehand and then feed in. And so that seems to be a little bit better. Cool. Yes, thank you, everyone. I guess we have to drop now, but I really appreciate all these questions. They were very helpful. They keep me on my toes. Yes, that's the one, Stephen. All righty. I think that's it. Thanks a lot, Seth, and thanks to everyone for your time today. And hope to see you soon. Bye. Muchísimas gracias, igual.